So I hope my screen is visible to you, I guess.
Yes, sir, it is.
Perfect. So, yeah, so initially we would warm up with, since this being a slightly newer area, so we would try to motivate why do we need to study this. So, you have learned transport, you might have learned reaction engineering, you might have learned some heat transfer, so on and so forth, our core courses. So the first aspect that we are trying to see, why do we need to study process control as a core course? So we'll see what is this, how does it help in terms of, of course, chemical engineering is all about process and process plants, how process control as a paradigm would help us to achieve that. So just see, the most important aspect we are looking here is we are trying to see process not as isolated unit, but as process plants, in the sense that you may, so of course, in the other, maybe in the other unit operations, for instance, heat transfer or other unit, the other subjects that are reaction engineering, we might try to see isolated units. For instance, we would like to see heat exchangers, or maybe you may like to see a reactor, fine. Then, of course, if it's a fluid mechanics problem, okay. So there is some lag, I guess. Give me a minute. Yeah, it is done. And maybe if you are looking at the transport, right? Maybe mass transfer or heat transfer. For instance, heat transfer, you might look at another individual unit, for instance, distillation, fine. And of course, if it is a fluid mechanics, you may talk about pipe flow and so on and so forth. So what I am trying to say, we were focusing mostly on individual unit design or how it works. What process control is talking about the process plan as a whole. So you are trying to see the concerted, what I would say, concerted effect effort of various process units which are working together. So all our arguments would make the most sense when we are dealing with a process plan. So of course, when you are a process plant, then we are talking about an end-to-end business. So every plant is not running for what just for charity. It has to run to make profit. Of course, satisfying various other conditions. Eventually, we are talking about an enterprise. So there are two aspects of enterprise. Right? First of all, the quality of the output, so which talks about performance requirements. So why? Because unless you are not giving a good product in the market, you are out of the competition. And so which essentially means that you need to perform more and more. You need to push your quality towards the boundary. Since we are dealing with manufacturing system, okay, so the manufacturing system is essentially is antagonist to technically antagonist to environment. So whatever you do, there would be footprints, emissions, okay, and also you may have to work with tighter safety regulations because you are working with a enterprise with maybe X number of employees and which has safety critical equipment. So with the safety critical equipment. This could be reactor, this could be heat exchangers, and of course we are not working it, we are not operating them in the normal conditions. You may have to take the temperature up, temperature down, high pressure. So basically you have to deal with high safety critical conditions. Okay, then eventually, so performance, of course, you have to The next is you have to supply them into market. So which is whose economic conditions are varying extremely dynamic. For instance, pre-COVID, the economic demand was something. During the COVID, the economic demand was something. During post-COVID, it could be something else. So basically, what we are trying to say is, when you look the process plant operation as a whole, then it's a business game. You are not talking about just designing something. You are just not talking about just opening something. You're just not talking about measuring something. It's not like a laboratory experiment. So eventually, to satisfy all of this, okay, what would eventually happen? You may have to add various retrofitting. So this would eventually make the whole process complex, because you have to satisfy the performance, environment, safety, market, so on and so forth. And you would see that there are n. So see, you are not talking about one unit. There may be units which are connected. So you would and because your raw materials would start from unit 1, then it would percolate, and it may you go to n number of units. You don't know that. So this may be the output. This may be your input, and this may be your output. Slot out. And what eventually can happen? Okay, and input can also be from multiple units. Let me tell you an example. Okay, so see, of course, you will have n number of units. Okay, so you may this may be your raw material. Okay, okay, this may be some pre-processing. Okay, for instance, basic pre-processing. Then it might go to. I'm talking about simple. So this may be a pre-cleaning. Before, if you need to something, then it might go to a reactor. Then it may go to a separator. Okay, and each of this reactor may have heat exchangers in line. So reactor might be connected with heat exchangers to maintain necessary temperatures, so on and so forth. Same with separation. Separation, you may have something else. For instance, there may be co-current flow of something to separate. There may be counter-current flow of something to separate. And finally, maybe after X such transformation, you would get eventually the product which you are selling into the market. And as you would really see, each of these individual units are getting their inputs from the precedent unit. Of course, the raw material may go to the unit 1, then it may go to the unit 2, is of course connected with 2, so on and so forth. Eventually, unit n is definitely connected to n minus 1. So the problem here is that, let's say if something bad happened here. For instance, let's say the heat exchanger got tripped. Okay, what is going to happen? Your reactor temperature could go up. Okay, that eventually would happen. You might start sending the undesirable product to the separator. Then separator load would increase, because you need to have more pure output. So this would possibly, if there is a pump here, and if you're sending some what you call absorption liquid, the load of the pump goes up. Eventually, the whole system would go in a what I would say, would be under tremendous stress. Fine. So what we are trying to say here is that, so it is, if there is due to this enormous complexity, it is very difficult to prevent the chain of transmission of disturbances. Disturbances could be anything, as I told. It could be just as simple as switching off your pump or tripping off your pump. So it's impossible for one person or maybe even a group of people to manually manage this. Let's look at here. Okay, so there are n units, and let's say every unit there are, see, each of this unit would be doing some certain unit process or some unit operation, and there are multiple parameters associated with it. For instance, you may need to have a desired temperature, you may need to have a desired pressure, you may need to have some desired flow rate. Okay, then for instance, you need to have a catalyst with certain packing efficiency, void fraction. So see, when you start listing the parameters, right? So it's eventually it's going to be a very it's eventually it's going to be a very difficult thing to kind of bookkeep. And as a man, so even it's even difficult to do it manually. Bookkeeping itself is difficult, and manual bookkeeping would make it further difficult. Okay, so what is the solution to an automation? So what will you do? What would happen in automation? Of course, things are controlled remotely. Okay, and you only need to have minimal manual intervention. You cannot get rid of manual intervention at any point of time. Even if you are using a driverless car, at some point you may need to do a manual intervention. So manual intervention is impossible to leave from the wholesale, but you will be able to reduce the level of manual intervention. Okay, so why? What's the advantage of that? So if you reduce the level of manual intervention, then the level of subjectivity is getting reduced. So what is the advantage of level of subjectivity? Humans are very subjective. So his or her decision would be mostly dependent upon uh, various factors, including the emotions at that particular time. So it's important to take away all such, what I would say, a subjective decision making, because you are playing with you are playing with a huge market wherein your decision 1% error in decision making can even result in loss of millions of dollars. So again, take the example of an aircraft. So most of the time when you fly, an aircraft fly, the manual intervention mostly when is you during takeoff and landing. Because these are inevitable. Like you will have to do something. So once it is in the desired path, most of the things would be controlled by autopilot. So the same way, you need to have some level of manual intervention, which you cannot eliminate, but reduce that so that the level of subjectivity in the overall operation is reduced, so that, okay, still you are able to achieve the conditions such as safety, environment benign, okay, market driven, and being top class in terms of the performance. So the simplest way is you have to automate as much as possible. Of course, there is some cost incurred with this, because when you automate means what? You will have to invest a lot in terms of infrastructure, but the return would be in terms of the reduced labor. So you don't, so see, if you are having, let's say, 10 units, and if you are operating it manually, you may have to, let's say, employ 10 people per unit. So you are talking about 200 employees. When you automate, you still, of course, you need to keep a threshold number, but you can cut down the what you call cost in terms of uh, what you call human resource. So basically, this is overall a trade-off business. So but the clear advantage comes in because when the safety regulation you will be able to mostly satisfy, because the decisions are pre-coded, what would happen? Let's say the temperature goes up. If it is not, no, if it is an auto-coded instruction, the systems will be able to act much faster than human reflex. So this is of course true for any automation. So in process plan, this become most critical. So automation, as I told, is an interfacing area, right? Many of you, your colleagues, other students would also be learning automation in different way. For instance, electrical people might be learning this. They would learn it as control theory. I would assume mechanical people would also learn little bit because they would need to do the production and some aspect of that, as I told in CS. So eventually everybody would try to employ this because automation is a very general keyword. Even you could automate your business, so that has nothing to do with process control. But the automation of the overall process plan is more non-trivial because you are dealing with systems. Okay, you are dealing with human in the loop. Okay, you are dealing with variety of condition, so on and so forth. So what I am trying to do is a non-trivial problem with which is difficult to solve by a human as an individual. So it's better to do an automation. So if let's say if you are going to go with an automation, so eventually what is that we need to do? So anyway, you're ready to you are anyway decided to invest. Okay, so what is the best thing that you would be able to do? So you should the control system or whatever the process control system will be able to maintain a process at the desired operating condition, which means that you have lesser trouble, of course, safely and efficiently, because you cannot uh, keeping what I would say, keeping it safe does not mean that you can also lose out on the dollars. So here it has to be meeting your what you call economical equation, and of course environmental regulations. So you would see the carbon footprint recent what I would say news article regarding IPCC wherein the emissions where we are leading to. So it is sure that over and over the environmental norms are going to be stringent. It would also bring in lot of stress, and of course your most importantly the quality. If you are out, if your quality is bad, you are out of the market in that moment. Let's say let's say you're making a drug and it has FDA approval. If even if a mild quality failure could lead to your uh, cancellation of your permit for. So again, so this problem is still okay to deal with if you are dealing with a smaller system, but most of our process plants, the scale of the plant is not small. You would be having, I hope you might have gone and visited some many industries, or you might have done some training or internship at some process plant. You would see that how the, the number of units that you want to deal with. Okay, so so this is our motivation, and you should, so what eventually have you will be doing, you would have a control system. So forget about this word feedback. We will learn this in a more detailed fashion. So what is the advantage? So what are, so see, you have to do what you have to play a game, right? So what are available? Huh? So what is in your disposal, and what you would need to achieve? So you have to achieve for, of course, this is your problem statement. You need to achieve uh, process operation at the desired condition safely, etc., etc. Huh? And what all things are available to you? Okay, you can. by a so let's say by blanket understanding, by doing a process control system would achieve. So you bought your process control system, but process control system is also needs some guidance. So what is its degree of freedom to play with? So there are sensors in the plant, various sensors. Consider any example that you would like to do an automation. For instance, driverless car. Okay, there are a lot of sensors that track the GPS information, road traffic information, proximity to the nearest vehicle. Similarly, in the process plant, you have all of these units that we have seen is equipped with various sensors that measures key variables. So you cannot measure n number of variables, all the variables, because there is a trade-off in terms of economy. Because see, if you could install all the sensors, then see there is so in an industry it's always an optimization of capex and OpEx. So let's say if you could install the sensors one time and if it saves your job, then still it makes sense to invest. But the sensors is also are also having wear and tear. Some of them would stop working. So there is also huge operating cost or maintenance cost associated with it. So it's not fair or it's not what I would say economical to install the sensors wherever possible, or you install all sensors to measure everything that's coming out of the process. But you can still install some sensors to get key process variables. How do you define that? Is of course the job of a process control engineer. What is the key process variable? You need to understand. Okay, then these key process variables would be fed into the control system, and they would be able. So this key process variable also, some of them. So see, the process variable measuring them would not be helpful, correct? So you should be able to do some changes on it so that your desired output is maintained. So, for instance, if you need to reduce the temperature, you may need to increase the coolant flow rate. Okay, so you would be able to take key process variable, identify how many, what is your, what I would say, how are these amenable to you in terms of playing around with. Some of them you may not be able to do anything. Some of them you will have a room to play with, and you use them to manipulate. So I will use the keyword now. I can manipulate. These variables are called manipulate to control the desired variable. So there are two things. One is manipulated variable. So manipulated variables are used to control the controlled variable. So what is a control variable? It could be a proxy variable corresponding to product quality, or maybe a true variable, for instance, temperature or pressure whatsoever. So this is the way, this is the basic premise of a process control system works. And as I told you also yesterday, so we have to learn process dynamics to learn process control. Why? Because see, if we are dealing with real time, consider you're driving a car, a driverless car. You have to take decision with respect to time, every instant, every second, or even every millisecond. So you are working with a system that is fully in unsteady state condition. Okay, while unsteady state, or you call it transient, or even dynamic. All of these words are namesake, so you may be able to use any of this to represent the overall strategy. While when you design, they're all at steady state. So you might not be using this dynamic information when you design a heat exchanger, because it would be designed for a maximum capacity, assuming this is the maximum value it takes. So they are all steady state. So you whatever you have learned would be mostly over the design or the design equilibrium relations, especially equilibrium is a steady state condition. So yeah, you cannot approach this problem with that context. So things are all dynamic. So you probably need to look to the problem in a dynamic framework. So you have to learn a system. Of course, the process systems won't change. The way you approach would change. You should be able to model them dynamically. Sorry. So all the operations in a process plant is highly dynamic. I don't see any case it would be steady state. So while you design, you will do it for steady state. Otherwise, you will not be able to design. So what you would do, you would consider a maximum operating condition beyond which for maximum capacity condition, and you would design. So assuming that anything below this capacity, things would work well. And when it when it close to the full capacity, so you will not operate anyway close to the full capacity or exceed the capacity. So that factor of safety is included while designing. But when you run an operation, you will have to look at how it is varying with respect to time. For instance, startups, shutdowns, everything is transient. In startup, your condition would change from time to time. Shutdown, your conditions would change from time to time. And so on and so forth. So that's why we need to really learn the dynamics before we embark onto control. So learn the dynamics, be clear, because you need to, all your decisions for control is dependent upon the dynamics. So dynamics is what dictates you to take a particular control. So control, so eventually control means it's an action, okay. So this dynamics is what you need to dictate what action should be taken. And this action would again drive you to another dynamic condition. So this is a ever running loop which is feeding back and forth. So before we go ahead, any questions at the moment? So if you have some queries, you may also keep writing in the chat. So maybe after some time when I take a pause, I'll be able to read it and give you feedback. But if you need to instantly shoot questions, that is also welcome. Anything is fine. Any questions so far at the moment? I hope I am audible to all of you.
Yes, sir, you're audible.
So there's a slight audio issue that some people are reporting that your voice is a bit breaking in between, just in between because of some white.
Okay, so whenever that happens, do let me know immediately. I hope it is fine now.
I'll just ask with a few kids who reported it.
Okay, so you give me an update. Meanwhile, I'll go. So eventually, so what all? So you will have to now see your what you call decision space. Okay, you will have to deal with process. Okay, so which does material can also do a conversion from feed material to product. And you would have chemical or physical operation. Chemical operation would imply a reactor. Physical operation would do cleaning, separation, heat exchange, so on and so forth. And see, so now you will have to see the level of complexity you will have to deal with. The process could be continuous. and also should be batch. So what is the difference between batch and continuous operation? You might have done your CRE lab. So continuous, it is ever increasing. For instance, CSTR is a clean example. Batch, you charge everything and you let a fixed time. So most likely it is will be a fixed time batch. You charge all your speed, huh? Close the knob, everything, and you operate it for fixed time. So unlike continuous operation, so none of them would eventually lead a steady state. Continuous operation would lead to what is known as quasi steady state. What do you mean by quasi? I will talk about that. While batch process will not attain any steady state, fully unsteady state. Quasi steady state means that, let's say you are looking at a temperature with respect to time. For some point of the window, it might look to be steady, but like you would see, it is varying. So if you look at the delta time, it may look to be steady. So this is precise steady, and batch would be fully unsteady. So you will have to, so depend upon your decision making, your problem that you need to work on. The decision making would also be different. So here you may have more room, but here you will have less room, so on and so forth. Is that audio issue is still there, or you are okay with that?
So the students say that it's better now.
Okay. So let us know if there is a problem so that I can check any network issue and so on and so forth. Okay, so let's see. Hopefully this is clear to all of you. So then let us see some key terminologies or some key words that you would need to use in the context of process control. One is, of course, our requirement, controlled variables. It is generally called as CV. So if you are working in industry, they'll say nobody will say control variable. They'll say CV. What is a CV? Of course, not your kind of a CV. It is control variable. So it is that process variable that to be controlled. Okay, and the desired value of the control variable is called a set point. People might use a set point or maybe use a term called set hyphen point, so on and so forth. What is a set point? We'll see. So let's say if you need to operate a reactor temperature with respect to time again. So unlike all other systems, we would talk about with respect to time. And this is T. You will have a T reference. This is your operating temperature that you need to. And your physical temperature will not be Tref at any point of time. It would be okay. So if you are starting from, so let's say this is, let's say 350 degree Kelvin. When you start the system, of course, it would be in the ambient condition somewhere here. Then it will go up by means of something, or assuming that you are doing some changes. Okay, then this is your set point. Fine, and Tref, which is T, so which is that you need to control, this would be your control variable. Fine, and so set point, as I told, set points will not be, so your reference will not be equal to set point. There would be some variability, as I told you, would keep on happening due to various things. And let us say you are using coolant flow rate, because temperature, you need to increase or decrease by means of coolant flow, or maybe a heating line, whichever, it's up to you in whichever plant you are working, whichever option, whichever what is the space for your decision, you might use one of this. to increase or decrease the heat. So let's say we have a reactor here, nice reactor, maybe let's say this here, feed in, feed out. So I'll say Fi, feed in, feed out, and it is jacketed. You heard about this jacketed CSTR because we need to measure some have some temperature. So there is some heating or cooling, whichever line that is. So this is, let me try to use it in a different color maybe. So this blue line indicates the heating or cooling line, while the white line indicates the product part. And your optimal conversion or optimal yield would be happening at a temperature because all the reactions are immediately uh, or uh, or has some function or is a function has some relation with respect to temperature, starting from your Arrhenius condition, so on and so forth. So you have some room, you can play around with this particle heating or cooling line to maintain the temperature. So let's say that is what you are going to do. So this is, so the temperature of this inside the reactor is your control variable, fine, and the coolant flow. I'll say CF, coolant flow, or maybe heating liquid, whatever you would like to call, would be your manipulated variable. They'll call it as MV. So, so eventually, what are the things that you would eventually result in the output concentration? So eventually, you are looking at the purity of the product with respect to time. Again, with respect to time, that's most important. And let's say you are manufacturing a drug. So then most likely your purity requirement would be 99.5 or above. And this is the eventual. So what is that is expected while keeping the temperature at the desired level, the reaction would happen and eventually you would get a purity or yield, whatever, as necessary. Fine. So you can play around with manipulated variable, which is the coolant flow rate to achieve all of this. Let's say you have got a bad feed one day, because eventually it's all market driven, and also it's also depend upon economics. Let's say sometimes you are decided to take a luck in buying a low quality feed, low quality raw material. Low quality in the sense, I will not say it is really low quality. So let's say if you are operating a refinery, you would get crudes. So there are, if you see that people would try to say sweet crude and sour crude. Some of them would be really high in sulfur content. Some of them would be moderately affected with sulfur. Some would be very clean. So let's say, okay, so you would anyway operate within your restriction, but you got a reasonably poor feed. Then what would happen? It would start disrupting your system. Huh? So what is the feed quality or feed quality started disrupting because you require very high quality output, but somehow due to the uncertainty in the feed, your products start going little less, little maybe, or keeping there is some oscillation. So what is happening? Your whole system or whole process getting disturbed due to a disturbance that is originated somewhere inside. So in this case, it is a feed quality. So such variables that affect are called disturbance variable, which is called DV. Some of these disturbance variables are measured, some of them are not. So disturbance variable could be further measured or unmeasured. What do you mean by that? Measured means you could quantify the variability, while unmeasured there is no means to quantify the variability. So most of the case, some also see in the crude case you may be able to quantify it, because while when you buy it, you do a feed check. So you would measure and it would be a calibrated uh, thought that okay, so my system is going to get disturbed because I have a poor crude. Just a second. Okay, I'm sorry about that. Uh, so we were talking about measured and unmeasured disturbance variable. So how do you measure? Because there may be some analytical way to measure. Because when you are buying a feed, you should be able to check. There are analytical way to check the quality, and so on and so forth. Let's say you are sending this coolant flow rate into the plant. Right? So this is your coolant flow. And you are expecting, so how do you send the coolant? Because this requires a circulation, right? It would go to some, and some from it will go back and things like that. And you will have a pump here. The pumpers what do this circulation, help you to do the circulation. Fine. So let's say your RPM of the pump keep on decreasing. The pump, of course, how do you measure? So how do you detect the pump so output flow rate? The pump specification of the pump would be in terms of output flow rate. And this is possibly by means of the rotation of the impeller and so on and so forth. And this would, and that impeller would be connected to a shaft, to a motor, and that would be running at certain RPM. So let's say your rated RPM is, let's say, X, maybe 100 RPM, 200 RPM, whatsoever. Okay, which is what you would expect, because this is, you bought your pump here and you would expect that it would start delivering the flow at this particular rate. Over that time, or due to some malfunction, this has become 190 RPM, or maybe 180 RPM over the time. How do you come to know? Because you don't have a measurement to check the flow rate anywhere. You would assume that I have bought a pump with a rated capacity and the pump is expected to deliver that particular flow. So what is going to happen? Your coolant flow rate, which you would expect maybe at maybe 10 liter per hour, might keep on varying. So it may be now 9.5 or maybe 9.2, so on and so forth. So that's brought in the variability. So how do you, so and there is no way to measure this. So such conditions things become unmeasured. It is a disturbance, but unmeasured disturbance. How do you come to know that there's a disturbance? When you start seeing your temperature, okay, you would see that the temperature variability is high. So you can go back and check. That's only way if things are all working fine. The temperature is of course just controlled by the coolant. So there is some variability in the control, but you cannot. There is no clue on how to get that information, exact information, unless you put a flow measurement here. Then you will be able to get it. So as I told, when you do this trade-off in terms of sensor placement, some of the sensors you won't deliberately place to save economics. Some place you will have to keep. At the points, the checkpoints where you don't keep a sensor for measurement, that would become eventually your unmeasured disturbances. Okay. So I think that is what I wanted to say here. Manipulated variable. You can read the notes. Manipulated variables, disturbance variable. Okay, so disturbance variable could also be due to ambient conditions. For instance, the sudden change in the temperature. Okay, so your overall temperature. So this may not be happen in a tropical country. It could happen somewhere in North America and or Europe. Let's say in a fine day, your temperature, let's say, is close to 30 degrees C. Huh? And in the afternoon, it starts snowing. So it went to minus 2 degrees C. So you might have set your whole operation considering that it would, of course, this is a summer time, or you would like it is expected to have lesser variability in the temperature. Of course, 30-degree may not be the temperature. You would expect a plus or minus 5 degree, but like you see now there is a minus 32 degree down. So these kind of things you may not be able to predict. Could be sometimes your weather forecast might not give you this. If you got to know by weather forecast, it would again become a measured variable, measured disturbance. Then you are prepared to deal with it. While in this case you are not. Okay, so the key aspect. Okay, so let's say you are hired as a process control engineer or a process control specialist in a industry. Your and you have been asked to design. So they are coming up with a new plan. Okay, and you are in charge of the process control team. And the key aspect, your first major job is to identify these three. What are the control variables? What are the manipulated variables? What are the disturbance variables? So all your decision making would depend upon the clusters of these variables. That's the problem. 14. We go a couple of more slides. So again, so let's consider an example which is very similar to that I have told you before. It's of course a reactor. In fact, this is just a mixer. There's no reaction happening, and you have two feeds. This is the feed 1, and this is the feed 2, and this is your output. Okay, feed 1 is so. What is happening is you are having a mixed feed of A and B coming to the mixer, and you have a pure feed of A coming to the mixer, which you have a way to control. So, okay, how do you control? We will see. But you can control at the moment. Assume that you will be able to control it by means of control valve, controls. We will see that about. And W1 is the mass flow rate of your feed 1, W2 is the mass flow rate of feed 2. X1 and X2 are the mass fraction of component A in the feed, okay? And we would assume that here the flow rate is constant, which is W1, because you have got somewhere you have kept a pump, as I told, and the pump will start giving you a constant flow rate, okay? While so the second line W2, you will be able to do some control. By means you are a process control person, you can play around with basically. And also it is assumed that X2, the feed 2 is pure A. And what is that you need? Okay, you need to have the output concentration to be a desired value. That's basically the mixing problem, right? So there are feeds in, feed out, and your output should have a desired composition. So the control variable would be X, which is the output composition, and the manipulated variable is W2 because you are playing with it, while W1 you cannot play because it's at the constant flow rate, but you don't know the composition of X1. X1 composition can vary, but here the composition is fixed. You see the gain. So here you are feeding pure feed, but its flow rate can be changed. While in the other side, its flow rate is fixed, but concentration is variable. So what is the disturbance variable? Because you don't know the value of X1, because here is so here only at feed 2 only you know the value of X2, because you say that it's pure means it's pure. So while X1 you only know that it's X1, you don't know the value. So this becomes the disturbance variable. And manipulated variable, because we are adjusting the flow rate, it becomes W2. Okay, so any questions at the moment? Any questions at the moment?
So can you explain again why x1 is the disturbance variable?
Why X1 is a disturbance variable? Okay, so see X1, if you look at the system, okay, you don't have any information regarding the composition of X1. While X2 is pure feed. Pure feed means what? Its concentration is known to you, correct? While in the stream W1, its flow rate is known to you. You are fixing the flow rate, and you don't have any idea what is this composition is. If it's known to you, then it is not.
Okay, sir, yes.
Unknown. It's unknown, so its variability can make the overall what you call output concentration affected. So it's become disturbance variable. Okay, so now I'll try to see what is the. I'll see the. We will now try to see that if maybe we have 5 minutes. Okay, we'll quickly do both those things. Okay, so I will quickly take these two slides and we'll wind up. So what is the fundamental difference between the design and control? That is what I am going to tell you. Okay, so design, if you want to design, what they would do, so designer would do, okay, they do an overall balance. So the problem is, what is the nominal value? If the nominal value of X is X bar 1, X1 is X bar 1, this is X1 is X bar 1. What is the nominal value of W2 is required to produce the desired output concentration XST. XST, which is outlet concentration X, which is equal to XST. So this is how you design a system, because everything is under steady state. So the overall balance is what? Input plus output minus accumulation. There's no what you call so there are two inputs, W1, W2, okay, outputs. Assuming there are no accumulation, so this would be equal to 0. So let's say you are given component A, you do a component A balance, W1 bar. So this bar indicating that specific value, W bar 1 X1, W bar 2 X2 minus W bar X is equal to 0. Okay, and and it is given that feed 2 is pure, so which means X2 bar 1 is equal to 1. So when you rearrange, you will get the value of W2 bar, and this X bar is kept to be XSP as part of the problem. That's all. So you can rearrange and very nicely come up with this algebraic equation. So this is how the design works. So you are not worried about how the tank level changes, tank concentration changes, anything. Do a balance, find out and isolate the variable. In contrast, okay, so as I told, X1 is a disturbance variable. If X1 is varies with respect to time, but again, you're running the company, you cannot be taken for granted. X1 is varying, but you have to sell the product. So you have to take action so that your output X is close to XSP, that is your desired vertical value as dictated by your customer. Let's say you are making a drug 99.5% or 100, close to that. You are saying that this is what you need to do. So your customer is telling you this. And your X1 has started varying. So control problems comes in there, which is nowhere. So that information is not taken into account in this design. So design is assuming okay, everything is under nominal conditions. So see, this word is very important. Nominal, how things work. While in control, okay, your X1 would vary because you are purchasing this from someone. His feed quality went bad. So what you can do, you cannot take it just like that. Then why? Because your product quality would go bad, and as a result, your sometimes so your specification will go bad, and you may be revoked to sell this product again. So you'll have to take an action. So what you could do, okay, and there is no control on this, so it is coming from somewhere. But you can do some control from your end. So this is, I would say, this is not at your control. Assume, okay, this is what. Assume that this is not at your control at the moment. So what you can do, you can measure this. Okay, you can measure the quality and do a correction and do a change W2, still make that access closed. Fine. Okay, so now let's say this is under control. As I told, then it's become measured. Now I was talking about the case of unmeasured. Let's say you have got you keep a sensor here, okay, to measure the, okay. Then what you can do, you can measure X1 and adjust W2 because so what is the advantage of W2? You already has a controlling mechanism. You can change, increase or decrease, so that still X is equal to X2. Okay, so and if you are rich enough, you keep both. You keep both the sensors, measure both X1 and X and X1, and adjust W2. Or use a large tank. What do you mean by using a large tank? Which means that there is no scope of disturbance. Less. So basically, you increase the capacity or damp the unwanted effect. What is the problem with that? Large tank means large material of construction, which means large capex. So what all things you can do is what we need to see from this point, and you will come to know. So I'll stop at this point and we'll continue on Friday. And this Friday, we can still keep a doubt class if necessary. Otherwise, we'll leave it. Any questions so far? Any questions? Any feedback? Things are okay? Shall I unshare the screen?
Sure, sir. I'll stop the recording as well.
Thank you. Thanks a lot. See you guys on Friday. Bye.
Thank you, sir.